Okay folks, this is the second video for section 4.2. The first one is over on Loom. And in that video, I introduced the Rolle's theorem and then generalized that to the mean value theorem. So as a reminder, the mean value theorem basically says that if you look at a secant line between 2 points on a smooth continuous function, it's got to be both, in this case, it's got to be both smooth and continuous, so no cusps and corners, otherwise that breaks the theorem. It says that if you look at a secant line, that slope of that secant line, you're guaranteed to be able to find some point or points within the interval that achieve a tangent line of the same slope. So I'm just going to show you a physical demonstration of this theorem. So here are two examples, all right? I've got my ruler here. So first things first, let's go ahead and, in each case, A and B are identified, okay? So in this case, first I'm going to go ahead and draw my secant line. Doobity-doop. There's a nice secant line in purple. Secant. So that's the average rate of change for this function on the interval a to b, all right? So now what I want to do is try to find a tangent line which is going to be parallel to this secant line. So I'm going to move my ruler away and keep it parallel. And what I'm looking for is a point on the graph where the line looks tangent. So that's going to occur right about there. So let's see if I can, you can see it's just touching the edge of the curve right there in a tangent way. So if I do that, I've got a parallel line parallel to my secant line, so it's got the same slope, and the point of tangency is right here. So that is one value C, where the instantaneous rate of change is the same value as the average rate of change on this interval. In other words, the tangent slope is the same as the secant slope. So there's another one though. Sometimes this can happen in more than one place. If I take my ruler and move it the other direction, you're going to see we will find another point right up here. There we go, right about there, where I can make a line parallel to the secant line. There we go. And it's tangent to my curve at this point right here. So that x value is another value, C. I'll call this C1, and this will be C2. So here we have two possible values in the interval that satisfy the mean value theorem. Okay, there's 2 points where the instantaneous rate of change is the same. Let's do it again. In this example over here, first of all, I'll draw my secant line. Here we go. That's my secant line. And then we'll take that secant line. It looks like if I move it this direction over here, I'm not going to hit any tangent points. But if I move it the other way, here, let me pull it up like that. If I move it this way, all right, I hit a tangent point almost right away, right here at this point on the curve there. It's kind of hard to see, but let me draw the line. There we go. You can see there's a tangent point right there. So there's a C value, right? And let's keep moving away. I think there's going to be more up here. Right? The next one we'll find is about, oh man, this is total coincidence. I'm kind of shocked. It looks like those 2 points share a tangent line. Pretty close. I mean, maybe they're slightly off, but they're very close to each other. So that's kind of coincidence. I didn't mean for that to happen. But it looks like this this slope gets attained both here and here. So here we have 3 different points, C1, C2, and C3, where the instantaneous rate of change is the same. So it occurs to me, I hadn't planned this, but it occurs to me that it might be good to show you an example of a situation where it doesn't work because one of the conditions is not met. So let's look at this graph. Okay. Now this is a continuous function, but it's not smooth because it has that cusp right there, right? So if I pick 2 points, like let's pick this point to be A, let's pick this point over here to be B, all right? Then we can draw our secant line, here, there to there. Okay, there's our secant. But now, with this example, if I If I start going like this, all right, I'm not tangent, not tangent, not tangent, not tangent. Am I ever going to be tangent? Is this ever going to be tangent, 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 tangent? No, because at that point right there, it's undefined, and then, well, that's it. I lost it. It's gone. Like, there's no more function. I went through the whole curve on this interval, and nowhere on this interval is there a point where the tangent line is going to have the same slope as the secant line. And that's because this does not meet the requirements of the mean value theorem. The mean value theorem is only valid if the function is continuous on the interval. So if you're going to apply the mean value theorem to make some sort of conclusion, you got to confirm first that you're working with a continuous function. If you don't know that you're working with a continuous function, then it would be not necessarily valid to apply the mean value theorem. So I hope that helps kind of wrap your head around what this theorem means. This is one of the most important theorems in calculus. There's a lot, there's a number of really important theorems, and this is one of them. We're not necessarily going to use it a ton, but theoretically, it is one of the big ones. You'll hear people talking about it occasionally.